Okay.
Where's John?
I don't know. We've already established, when I planned this thing out, I didn't expect we would get so far so easily. And so I thought it would take us almost a week to get to where we are. And therefore, I feel very happy that I can use the remaining days to do this. First, we've noticed and demonstrated by telling you what happens in an experiment without actually doing it, that ordinary ideas will not work. You've got to be very careful with the logic and so forth to handle what happens in real nature, in quantum, what we call, now we've developed a theory called quantum mechanics, which
What's unreal?
Nothing, it's just a mistaken phrase, okay?
It's a little early to start on that.
And, but we can't just be satisfied with saying that some particular set of ideas will not be satisfactory to describe the situation. The problem was to find out what set of ideas would be satisfactory to describe the situation. As a matter of fact, those ideas were discovered before the difficulties were discovered. And it's the ideas of quantum mechanics is that I want to describe now is a positive thing. It's a way that we actually use to make calculations and understand nature. Excuse me, to make calculations. We really don't understand it very well in the way that I've explained very carefully before, and I won't go over that all the time. I might say, make mistakes like that, talk about real nature, understanding real nature we are unable to do. At any rate, what I would like now to use in the remaining time is to, if I might try, to tell you actually what physicists do when they make calculations, so they can predict probabilities for events, right? And they predict correctly the probabilities of events for all the experiments, at least in a certain range where they know some things about electrons and photons and so forth, light and matter and chemistry and ordinary phenomena, not involving gravitation in detail or nuclear phenomena in, well, actually today I used to say those as excuses, but the nuclear phenomena are now probably under control too. But at any rate, for a vast array of phenomena, ordinary phenomena, we have this quantum theory. And as you might well expect, the quantum theory, I mean, as a result of our previous lectures, the quantum theory is crazy. It doesn't explain anything. It just gives you numbers. It gives you the right probabilities. And I'm making no excuse for that now because I've told you how funny real nature is. So I'd like now to describe what these funny guys, the physicists, actually have to do to make the calculations, and so that you would see what it looks like. In other words, what their view of the world really is. It's even more correct, a description of what the physicist does or how he looks at the world when he's making predictions. And so I start with the simplest phenomena that we can discuss. And the first one I want to start with is the phenomena of light. Early on, when light was being investigated by Newton, he thought that the light that came into the eye was like a rain of particles, like raindrops coming in. That more light meant more particles coming in. That light, he discovered, could be separated, white light, into different colors, light in the spectral arrangement. And one kind of color light would be one kind of raindrop, and another kind of color would be a different kind of raindrop, and so forth over the whole spectrum. And they would be running into the eye, and that if we would someday ever have sufficiently delicate instruments, we would presumably discover that it was like a pattering rather than a smooth current coming in. That if you tried to measure very weakly intense light, you would go click, 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 as the particles came raining down. It's as though we have a lot of rain on a big area because we, at the beginning, have crude scales and crude experiments, and we're trying to measure rain, and all we have is a pan 50 feet across. All we can measure is the weight of the water that comes down. We can't feel the individual drops. It's too subtle. But if we would take very fine 1 square centimeter tin and measure the force, we'd suddenly discover that it's irregular, that the rain is a bumpy business. That's what Newton expected, and he had this theory of particles. He also discovered a very interesting thing which we've talked about, the light from the soap bubbles or light from thin films. The brightness of reflection from a thin film depends upon how thick the film is. As the film gets thicker and thinner, it gets brighter and darker. That was hard for him to understand from the point of view of particles. Finally, a theory of waves was invented which explained that very easily, and we talked about that, how with the waves fitting into the space or not fitting in, we got strong or weak reflections from the surface. And so everything looked all right. It would be waves and not particles. And then the instruments got better and better until we measured light very precisely, like instead of the 50-yard thing to measure rain, it was 1 centimeter. And lo and behold, to our horror, it behaved like particles. The most sensitive instruments we have to measure light, for example, photomultipliers, discover when the light is weak that it's nothing but the multiplier goes off, bing, 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 as the particles seem to be coming in, okay? All the experiments, when you're measuring light carefully and when it's strong, there are so many particles coming in that the instrument sort of gets swamped and you can't be sure that they're individuals, but that's just technical, because if you put some kind of screens in or put more better instrument or whatever, then you discover again that they were individual particles. If you have a situation where the light is to go in if you have a situation where you have a source of light that's very weak and you put a photomultiplier, you get this individual clicks. If you had a room like or an area with a very weak light and had photomultipliers all around, then at any moment one will go off but not the others, or another will go off, a small number of bullets being shot out from a center. Then it would hit in one place or another place. So if you put photomultipliers all around, it checks. They don't both go off at the same time. They do that rarely, because if you're spitting bullets at random, maybe by accident 2 come out. But if you decrease the light intensity, that means make fewer photons, we call these bullets, per second, then the number of coincidences goes down as expected. And so we see that the light behaves exactly like particles. The different colored light red or blue or green and so forth, spectral light, correspond to particles of different energy. That is, the energy comes in lumps, and these lumps have different sizes for the different colored light. Now, what I want to describe, that caused, by the way, that caused a certain amount of trouble because it was hard to understand. In fact, virtually impossible to understand this effect that the reflection of light from layers of different thicknesses varies by using particles. And yet, when you measured it, it was particles. And that makes a problem, which I want to describe now. Yes?
For the go on, would it be possible to describe a photon, in physical space, what it would like, a specific photon, let's say sodium?
No. All we know is we get a click and a counter. Where it is or what it looks like, we have to decide on by the properties, okay? As you've already learned from the previous discussion, we're going to have a lot of trouble in picturing anything that we haven't directly measured. If we try to say how big a photon is, or how it's spread out, or what it looks like, we're going to get in some difficulty with some experiment. It isn't going to behave that way you'd expect. So you're going to be very disappointed, because it's going to be impossible for me to tell you how big a photon is, where it is, and so forth. Nevertheless, depending on your point of view, I'll tell you a series of crazy rules by which you can tell exactly what will happen in any experiment with photons. What's the chance that the multiplier will go off in this situation, that situation, without ever having been able to say what the photon looks like in a certain sense, okay? In the sense of some sort of model of waves in space. That's just a reflection in another level of the same difficulty that we had with the boxes that we were talking about last 3 days, that there just isn't any way to say, well, what is behind those buttons? What is it that makes the buttons make red and green? If we start to say that, we're going to get into difficulty. And it's exactly the same way. For this purpose or for that purpose, you can say what a photon looks like. And in that experiment, it'll work okay. But you can design another experiment, measure something different in the same circumstance, in which you won't be able to use your model to get it. It's much like this. If I always was pushing button number 1, never the 2 and 3, always measuring the same thing, that would make an easy problem. There would be not any complication in explaining what kinds of results we got. But if you allow that you might have measured something else, you'll see you're beginning to get into these puzzling difficulties. And so to make a complete theory, we cannot do it with a model. We can only make an incomplete theory. And what my purpose is today is to tell you the complete theory, not the incomplete approximations, okay? Because those are all in all the books and easy, and there's nothing, but they may not be easy, it depends on your mood, but they're there. And this fun of this is to talk about the way it really looks. Or we don't know what it looks like, what we really do. Okay? Okay? Now, what?
Somebody walked along this outside conversation.
Oh, yeah, right, okay. So we have to get the idea then that light, when we measure, we're going to measure all the time with these wonderful devices, which are photomultipliers. You might want to know how they work, actually. It's just technically a small thing. It's a light photon, when it hits certain materials like sodium surface or cesium, which is actually what's used, when the photon hits it, it knocks an electron out, an electrified particle. And then we could put another plate here. Let's say this is a minus and make this electrically plus. So the electron is accelerated and comes to this plate. One electron is rather difficult to measure. It's such a tiny amount that it's very, very difficult. So we need an amplifier. But the amplifier can be done automatically, because if you have this voltage, about 200 volts, when the electron plows into this piece of metal, it like makes a splash. There are electrons in the metal. And knocks a few of them out. Let's say on the average 5. It varies. Then we have another plate here that attracts those. And when those have got enough energy and bounce, each of these 5 hit this, then on the average they make 5. That makes 25. And then another plate and another plate, maybe 7, 8 plates. Each time multiplying by 3 or 4 or 5. And by the time you get up here, you got a tremendous host of electrons by this amplification process inside a vacuum. So one photon starts this whole thing going, and there's a like big avalanche, so to speak. And by the time you get to the last plate, there's so many electrons that it represents an almost macroscopic charge or current, and then we can go through normal amplifiers and electric circuits to light lights and tell us we've got a count.
Red or green.
Yeah, or whatever, to decide whether we have a count or not, okay? It goes off, click. Click is a loud noise. It requires a relay to kick something to make a noise. That relay takes a lot of current. That's amplified from here, and that was already the result of amplifying the result of one electron multiplying up. So all of the devices that we have, you must appreciate, are enormous amplifiers, because we're so big and the atoms and photons are so weak and small that to see any of these effects have to be very delicately, we have to amplify it a great deal. It's possible that this amplification, this perpetual amplification that's necessary, has a lot to do with our difficulty of understanding things on a small scale, because we only can see things on a small scale after they've been amplified in one way or another. But aside from that philosophical hokey poke, I now suppose that we have these photomultipliers. What does it mean when light is more or less intense? First, I told you what it meant, color. The amount of energy that this first electron is kicked out with depends upon the color of the light. I should have explained that. That was an interesting thing. If you, with light, it's a little hard to arrange, but you could do it with single atoms instead of a metal. But never mind. With a photon, you'll knock out an electron which originally had a certain energy. If you have, that was red light. If you have blue light, the electron that comes out has a higher energy. Each color light corresponds, therefore, to a photon of a certain energy, we say. The brighter light just means more photons. So when the light is weaker, it just means that there'll be less counts per second on the average, and brighter light is more counts per second. Of course, the counts don't come steady, pick, 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 but irregularly, accidentally, bonk, 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 and so forth. And we talk about the average number per second. Yeah?
When the different colored light comes, it would bump off an electron of a different energy level, so to speak.
A different energy.
So a red one would bump off
A faster, not as fast an electron as a blue one would. However, these devices, the photomultipliers, are not particularly, they don't care, because they accelerate the electron anyway, and they work with all the colors. They're built to do that. If you want to build one which is more sensitive to one or another color, you can, using either the energy or put something in the way so that only certain kind of photons can come out or something. What we're going to do now is to talk about, to make it easy for ourselves, we don't want to talk about too much at once. And so we'll suppose that all the light we're talking about is exactly one color. By the way, we tried to do something with the soap bubbles out there with looking at them in one color by putting them in a spectrum that was shining through one of those prisms outside. But it really was, from an experimental point of view, you liked it, but it was almost a failure because there was so much light coming from everywhere else. That is, light was coming through the windows other than the prism. And that light, you were also seeing reflected in the thing. Just like I can see in your eyeglasses now, reflections of lights all around, even though the most important light is that light. That's not the one that's lighting up, making the reflection for me in the eyeglasses. In the same way in those bubbles, although the most important light might have been, the brightest part might have been from the prism, we were seeing reflections from windows and other things, and it was all very complicated, and that's no way to do an experiment out of control like that. Much more satisfactory would be to have all the light of one color that's in the room so that you're studying it. And it's easy to arrange that. At night, they have in various places in the countryside and stuff, they have these yellow street lights. If you live where there's a yellow street light, that's a sodium light, and that emits light all of one color. Then take the soap bubble and blow it at night in front of that, and then you'll see the bands I'm talking, very fine. In fact, it's so good, the light, that you can take any kind of thin layered stuff, even very thin glass or something like that, and if you're careful and hold it just right, you can see very fine bands, even in a reasonable size thickness, because it's so accurate. But let me suppose then that we do have light, like from sodium vapor, so that all the light I'm always going to talk about is always photons of exactly the same energy. We call it monochromatic, one color light. Good? Now we start out with the properties that have to do with intensity. The first thing we've been talking about is reflection from a surface. So suppose that we had a surface, say, of water or of glass, a single surface. Here's glass, and here's air, or vacuum, practically, we say. Now suppose that we have a source of light, and then we shine it this way, straight up and down. I'm making everything easy the first time, you know, the world is more complicated. We'll make a simple situation. Then, as everybody knows, the light goes down into the glass. And as everybody knows, you see a reflection also. That means that some light is reflected. It's partly reflected. If you'd measure so much energy per second coming down, that's the intensity of the light, you'll find that something like 4% is reflected by the glass and 96% goes through. Right? That's called partial reflection. And all of a sudden we have already our great difficulty. Because this is photons. If this is made very weak, and we put a photomultiplier here to look for the reflection, and we put a photomultiplier to look here whether there are photons coming this way. As a matter of fact, we can even measure when a photon leaves here, so we can even, but let's suppose that we forget that. We get the number of photons counted in here. Pip, 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 pip is much higher than in here. And this counts only 1/25 or 4% of all the photons that are coming out of here. 96% are counted here, okay? When the intensity is low enough, both of them never go off. If they do, it's a coincidence, you lower the intensity, it happens less often. So we say, they don't ordinarily go, one photon either arrives here or here. I could make this source so weak that one photon comes every few minutes. And we know at the speed of light that whatever it did, it finished before the next photon. So one photon at a time either lands here or lands here. You don't have 1/25 of a photon landing here. That's important. Just one photon either lands here or lands there. What then is partial reflection? It can only mean that the next time you try it, let's say the first one landed here, the second one landed here, but every once in a while, 1 out of 25, it comes here. It must be probabilistic. It comes, that's what happens. We discover that it's statistical and accidental, that the photon figures out whether to go here or here. If I could use that horrifying language, I don't really mean that. But it lands here or here, 1 out of 25. Okay, it's not so bad. But you say, how does the photon make up its mind whether to go here or here? In other words, what kind of a picture of a photon can I make so that I understand that a 25th of them go, 4% of them go up there? One possible theory. There are little spots here. they're so small we can't see them, little dots on the surface. They only cover 4% of the surface. If a photon happens to, usually, as it does, it doesn't hit one of those dots and goes right through. But once in a while it hits one of those dots and bounces back. That's my theory. It's all kind of deterministic. It depends on where these dots are. There were various arguments that Newton made to show that there were no dots. Yes?
Could that experiment be so, if that were, could that experiment be so carefully controlled that the photon would pass through virtually the same point in the glass each time?
No, you can't do that.
Because of the
When you make monochromatic light, you can't focus it any more sharply than about what's called the wavelength. No matter how you do it, you can't determine where it is better than a certain width if it's monochromatic. And so therefore you can't quite do what you want to do. Yeah. But Newton gave arguments which were great and very ingenious for his day about why there aren't any spots. I won't review them. They're historically interesting, though, to see how he could have deduced that at that time. However, I'll continue to describe the properties of reflection to a point where you'll see that the dot theory must be wrong anyhow. So I won't use Newton's argument. I'll use a different one. All right? Now, the fun of it is, so far, let me just tell you, it ain't going to be dots, and you'll see why it ain't going to be dots later on. No mechanism has ever been invented to explain what makes each one go up or go down. This is the kind of world we're in. We learned that we're going to be in that kind of a world. It's going to be probabilistic. All we're going to have is a theory that calculates the chances, and it doesn't determine for each photon which way it's going to go. It can't be done. All right? So, next experiment is but I wanted to explain what intensity was. It was the number of photons, and that therefore partial reflection is already a semi-mysterious process. Already we have trouble, even with partial reflection. But it gets more interesting when we realize, when we study what happens if we have thin layers. If we have a layer of glass that's only so thick, and we ask what the reflection is and how much is transmitted. Well, offhand you'd say 4% comes from the first surface, but when it gets to the second surface, it's possibly reflected again. As a matter of fact, it'll come out again another 4%. And so you'd say that the number that would come here would be 8%, or yeah, that's the best way, 8 out of 100 instead of 4 out of 100. And that 92% would come through. That's what you'd guess. And that seems to be right if you do the experiment carelessly and have the glass fairly thick and the edge is not perfect and slightly irregular. You don't measure everything very accurately. It'll look like that. But if you're very careful to make all the things very plain and flat and make it, especially if this is thin, you'll discover this is not what happened. What does happen? All right? See, there wouldn't be any problem with this. We could have the spots here and then the spots on the back of this surface. And if it missed the first spot, it has a chance to hit the second spot. That's why we think 8%, because it's 4% chance of hitting the first spot and almost 8. Of course, there's a slight correction. The first one would remove some, and so there'd be 96% to hit here, but that's almost 100%, so I just added. It's 4% of 96 plus 4. It's too complicated. It was just, roughly speaking, 8, okay? It mostly goes through. So, but what actually happens when we look at it is that we see that the amount of reflection of the light depends on the thickness. It gets bright and dark depending on the thickness. Just like we talked about oil colors. When we have a thin film of oil, we see colors. If we would do it with monochromatic light, light of one color, instead of seeing colors, we'd see bands of bright and dark, bright and dark. If we had two colors, the bright and dark bands would appear in different places on top of each other, and that superposition would make it a mixture of colors. And so we see a large number of different colors when we use white light on a film, but if we used, as Newton demonstrated, monochromatic light, any one color simply produces bands of light and dark. And these bands, as Newton found, depended simply on the thickness of the layer. And so we could measure how much is reflected depending on the thickness of the layer, and it comes out as follows. Now, these numbers are approximate. I'm doing things like taking 96% of 4% and calling it 4%, because it's nearly right, okay? So in that approximation, these numbers are. So this is the percentage of reflection, and this is the thickness. Right? Turns out if the thickness is 0, there's no reflection. Nice. No, there's nothing there, so there's no reflection. Then it builds up. As you thicken it, the amount of reflection goes up. You know how to read such a graph. That means at this thickness, there's this much reflection. And it goes up and climbs up to a height, which is in fact 16%. Unusual, it's not 8%. But then if you make it still thicker, it comes down again, and there's a thickness at which is 0 again. Then if you make it thicker, it goes up again to 16%, and then comes down again with a thickness that is 0 again. And this keeps on going. If I were to draw this on and on, it has been done experimentally for millions or hundreds of millions of these things, and it keeps right on going up and down, up and down, up and down as you keep this thickness increasing and increasing and increasing. If everything is done very carefully, then you can follow these ups and downs all the time. We talked about this. Different thicknesses reflect well, or another thickness doesn't reflect at all. Yes?
When the thickness is 0, the reflection is what was it?
No, it's 0.
It's not there.
It's not there.
Oh, you're not looking at film on a substrate, okay.
No, it's just a thin layer of glass. There's nothing underneath the glass. I should have explained that. This is also air. If there was water or something down here, it would be more complicated. I'm trying to make it easy. If there's no glass, there's no reflection. Nice. But actually, although it's nice, it would have been quite a mystery, because a very thin layer of glass, if there were spots on it, would make spots, and you'd have the 4%. And the fact that the bottom layer was very close to it wouldn't make any difference. Already we know it can't be spots. So, but the thing that's very exciting is that there's a certain thickness at which it's 0, and that repeats and repeats and repeats and repeats and repeats. Now, according to the wave theory, that turned out to be fairly beautiful but easy to explain, as that we talked about it, the waves bouncing from here and the waves bouncing from here would both come together with their crests opposite, crests and troughs, and cancel out. Whereas if the thickness was something else, then the timing being different, the crests would superpose, that is, they would add to each other and make more strength, and that corresponds to this case. You'll notice, by the way, that the average for great thicknesses over here, if the thickness is not exactly even and things are done sloppily, you get the average effect, which is the 8% that you expected. That's why large things, gross things, where you're not careful, produces the normal probabilities and everything like you would expect, let's call classical logic. But these funny ups and downs, these are called interference effects, which you need to be